Okay. Good evening, all the participants. A warm good evening to all. On behalf of Ramco Institute of Technology, Rajapalayam, I invite all the participants from various institutions and also on behalf of Ramco Institute of Technology, our principal, our head of department, our vice principal, and our other faculty members, and also our student members. We welcome all the participants. Uh, and also, I would like to give some introduction about our expert speaker, Mr. Dr. R. Vignesh. He had completed his PhD in biomaterials. He is very well versed in this particular field. He had vast experience for last 5 years. He actually uh, went through his PhD in CEG campus, Anna University, under the guidance of Dr. Saktinathan sir, Dean Tirunelveli, and also he is actually working in CG campus, Anna University, Chennai, and also he is vast experience in biomaterials. He had published more than 10 journal papers in biomaterials. He already completed his MTech, ME in MIT campus, Anna University, Chennai. Anna University, Chennai. I invite him for his particular talk because he actually one of my friend. He's my friend in MIT campus. He immediately accept my request and immediately uh, taking this opportunity. It is our opportunity to get this kind of expert speaker from CG campus, Anna University, Chennai. So I invite Dr. R. Vignesh sir to present about biomaterials and insight into biodegradable biomaterials. Thank you, sir. I once again welcome all the participants and expert speaker in this particular session. Thank you.
Thank you, Professor Maharajan. Am I audible to all?
Yes, sir.
Yeah,
Yeah, definitely, sir. Yes.
okay. Okay. Let me proceed. So, first of all, very thanks a lot to to Professor Maharajan. He called me 2 days back and asked me to deliver a lecture on this. So, initially, I was a little hesitant to do that, but he asked me to do it, so I'm very much happy to do it. So, as sir said, my PhD was in the field of degradable biomaterials. So, this topic may be new to some of you. So, so this entire lecture is just upon the basics of biomaterials. I am not going to go into any details of, expert details of what is happening in the field of biomaterials, but we'll touch upon various facts of biomaterials. What is biomaterial? What is the current scenario that is going on in biomaterials? And what are the future trends that we can expect? So like in the first slide, you can see the image of various implants. Like we have a hip joint over here, we have a rod for hip joints. So biomaterials basically means something which is which can be used inside a body, for a biological purpose. So in broader terms, if we speak, biomaterials is nothing else but implants that we use. So that can be both inside a body or outside the body. But overall, if we talk about biomaterials, if in a layman's perspective, I have to put it, biomaterial is nothing but the implants that we are using. So that can be your hip implants, your bone joints, your teeth implant, something in your heart, something in your eyes, anything. So that is the general perspective of a biomaterial. So this will be a very basic top talk. I have just 20 slides with me. So I'll be touching upon the various aspects of biomaterials. If this session is interesting to you, maybe in future we can have one more session in which I can talk about details of other things. But as of now, this will be a very basic talk. So like I said, we'll be talking about what is biomaterials. What is the current need for the biomaterials? Because we need to understand what actually is the need for biomaterials. And one of the basic important thing about biomaterials is the selection criteria. That how do we select a particular metal or a material which can act as a biomaterial? So that is a very important point that we need to understand. Then we will talk about the basic applications of biomaterials. Now, once we understand what biomaterial is, then we need to go a step further. And nowadays, the trend is going for degradable biomaterials. So then you may ask, what is degradable biomaterial? So then we'll talk about what is degradable biomaterial, what is the need for it, then how do we select materials for degradable biomaterials. and what is the current trend that is going worldwide or in the research field with regards to the degradable biomaterials. And finally, we'll just focus upon the cardiovascular biomaterials. Now, this was my main research field during my PhD. So maybe I can give you an insight about what is cardiovascular biomaterial or what are the cardiovascular diseases and so on. So this is a very wide interdisciplinary topic. So like we have working people in mechanical who work with electronic engineers for space industries or automobile industry anywhere. Similarly, when we talk about implants or when we talk about biomaterials, this is an interdisciplinary approach where we need input from doctors, from surgeons, from biotechnologists. So this is a kind of highly interdisciplinary area. So the scope of this topic is very vast, and there are interesting fields which you can explore in this. There are a lot of people who are working on this. A lot of expertise is going into this. So if you get into this, you will understand the need for this topic. This is the current need of the hour because a lot of people are we are facing the COVID situation here. I'm not including COVID in this into the biomaterials because that is entirely biotechnology oriented, but similar to that, biomaterial is a vast interdisciplinary topic. We have to go hand in hand with doctors, we have to go with biotechnologists, with surgeons, and so on. Okay, so what actually is a biomaterial? So in 1987, a term biomaterial, which was conceived in the society in a conference of Society of Biomaterials. So what they said is that it is a non-viable material used in medical devices intended to interact with biological systems. What does this mean? This means that we are putting something inside a body which will take up the position for which it was placed. Say, for example, I am putting something instead of bone. So, what that material should do is it should act in place of bone as a bone. So, why do we need that? Because bone is a strong material. It's a calcium phosphate. So, we need something which is as strong as bone. So, we are putting say titanium implant or stainless steel implant. So, that is our biomaterial over there. One of the main criteria for anything to be a biomaterial is called biocompatible. Now we cannot simply put anything inside a body because there is, we are a living organism. And there are a host of blood circulating around it. We have body fluids, we have plasma, and we have so much of things going inside it. So anything, if we randomly put anything, it may affect our daily routine, it may affect our bodily activities, and it may produce our toxic effects. So in any case we have to avoid that. So that is the meaning of biocompatible. Anything that we put inside a body, it should not produce any adverse effect. So what is biocompatibility? It is the ability of a material to perform with an appropriate host response in specific situation. So as I said, our body should not reject it. You might have heard about kidney transplants. In a lot of cases, there are scenes where the body rejects the kidney. Why? Because it's not compatible with the body. So even though a kidney is a natural body, it's an organic body. It's not like a metal or a polymer. It's an organic body. Yet the body has chances of rejecting it. So if a natural body is getting rejected, then think about man-made synthetic materials. The chances are very high. So we have to decide upon a material which is biocompatible. Pharmacologically inert. What does this mean? This means that it should not react with the body tissues. It should not react with the blood. It should not react with the plasma. Maybe I am putting, say, XYZ material inside a body, and that material is reactive to the hemoglobin present in the blood. So what will happen when the blood is in contact with that XYZ material? Some adverse reaction may occur, and that in turn will affect the whole biological system of our body. So we should have a material which is pharmacologically inert. Then it should supplement or replace a living tissue. Now we have seen cases, or you might have heard about cases of heart valve transplants. Now heart valves are totally biological, but nowadays we are having steel valves, bicuspid valves, tricuspid valves. We have all those things. So it is replacing our original valve inside a heart. So the biomaterial that we select should be sufficient or should be efficient enough to replace that heart valve. So that is the main idea of what is a biomaterial is. Now you may ask, sir, what is the need for a biomaterial? Why do we need it? To put into a simple point, if we need to survive, say someone faced a terrible accident or some kind of trauma, like on borders, people are facing so many peril issues, situations. Something might happen. So at that position, we need something which may support them. So what is the need for biomaterial? We need something to help us survive, because the ultimate goal of our life is what? To lead a healthy life. To do that, we need something which should support us. So the biomaterial, it should act as a replacement of a body part that has lost its function. Like I said, in case of hip joints, say someone had an accident and their hip joint is totally broken. So what we do, we'll put a titanium ball and we'll put titanium rods and we replace that entire hip portion. So even though, I mean, that may not be 100% efficient, but somehow it will give mobility to that injured person. So it will act as a replacement of that body part. Correct abnormalities. Now, there are cases like in spinal rods, or if it's a difficult one, we can say broken bones. We had an accident, my arm broke, it got into two pieces, or my collar joint broke out. So what we'll do is we'll put some plates. So it is correcting the abnormalities. So it is helping join all those broken pieces together and hold it together for some particular period of time. So it is helping us to correct the abnormalities. Improve function, like it clearly says, pacemakers. What is a pacemaker? It helps in regulating the heartbeat. So, I mean, in elderly people, sometimes due to the nervous dysfunction or something, the heart may not beat properly. So we have to give an extra stimulus to the heart to help it beat properly. So we can use pacemakers. Similarly, stents. Stents are, I mean, like one of the widely used cardiovascular material. Why? Because heart blockage. Stent is basically used to treat the problem of atherosclerosis, which is nothing but the deposition of fat inside your arteries. You must have heard it. He had a heart attack because there is a clogged arteries inside his heart. So to overcome that, we put stent. We'll talk about stent in detail in later slides. So this is like these things, pacemakers and stents, they are used to improve the function of a heart or of a body part. Assist in healing. Now, like it says sutures. We have internal sutures. Sometimes to stop the bleeding, we need to sew it. So sutures will help in your healing of that particular wound or particular region. Similarly, structural healing. Again, like I said, if bones are broken, we put in plates and screws to help join two bones. So that again is acting as a healing assistant over there. Stents again acts as healing assistant, because nowadays the research in the area of stents is extensive. You can see tremendous amount of literature is coming out every year in case of stents, because cardiovascular disease is becoming one of the major reasons for global death. Even cancer is second to cardiovascular diseases. So when we look at the broader perspective, the area of biomaterial is increasing, and we need more dynamic minds coming up to help solve these problems. Now, like I said before, selection criteria. We cannot simply put anything inside our body. We need something which we can justify putting it inside our body. Like now, most common is titanium implant. I'm sure no one would have guessed that titanium implant is going to be very easy or to put inside. Must have tried a lot of experiments beforehand, and then they might have concluded that okay, titanium is a very inert material; it will not react with the body and so on. So there are few steps that we need to follow in order to quantify any material as a suitable material for biomaterials. So this is the broader perspective. This is the broader way of characterizing any material. First of all, the basic steps. For example, say I am taking a material A. Now I want to verify whether A can be used inside a body or not. So what I'll do is I'll do the biological characterization. Irrespective of anything else, I'll simply take that material and I'll do a cell culture study. I'll see whether this material is inhibiting the growth of cells or not. If it is affecting the cell growth, then on the first stage itself, we'll reject it, because we do not want anything that will affect the cell growth. We need something, even if it's not helping the cell growth, it should not inhibit its growth. It should not affect the growth of a cell in any way. The first and foremost thing is biological characterization. So there are a lot of testing in biological characterization. We have cytotoxicity, we have hemolysis, we have antiplatelet addition, antimicrobial growth, antibacterial growth, so on. So there are a lot of biological characteristics, but the first and foremost is cytotoxicity that we carried out. We have ISO standards for this. We have ISO 10993, I guess, which is used for the biological characterization. Now, say our material A, it cleared the biological testing. It says, okay, we can use A as a suitable material. Then we need to understand where we can use that material. Do we need to go for a hip joint? Do we need to go for a teeth implant? Or do we need to use it as a stent or what? So based on the application, we will select the further mechanical testing. If we want it, say for example, a bone joint, it should have enough mechanical strength. The Young's modulus should be good enough to withstand compression. So here comes the role of a mechanical engineer. On the first step, we saw that a biotechnologist can help us, or a clinician can help us to quantify the biological characteristics. But now, when we talk about corrosion characteristics or mechanical characteristics, we need a mechanical engineer who can help us who can help us carry out the tensile testing, or bending, or structural analysis, and so on. So let's say we are going for a bone implant. Okay, so first of all, we characterize material A for biological testing and we pass that. Second is B, where we saw that, okay, we need a bone implant and we need, say, 50 gigapascal of Young's modulus and so on. But what we saw here is that, okay, our material A does not meet the standards of material characterization. It is having only 35 gigapascal. We need to improve. So what we'll do is either we'll go for alloying or we'll go for some other structural changes. So again, metallurgists can help us do that. But again, then we have to understand that we cannot simply alloy anything. If we are mixing material A with material B, we have to make sure that material B also does not create any biological issues. So I hope you guys understand that we have to follow this protocol to ensure that everything is within the safety level. Okay, let's say that our material passed both biological characterization and application-oriented characterization, that is mechanical characterization. Then we have to go for in vivo characterization. In vivo means within animal, within a living tissue. So like for corona also, I'm sure they must have carried out in vivo in some kind of animals first, or some kind of animal studies. Everything, every implant that we do, whether it's a bone implant, whether it's an eye implant, anything that is related to that can be used in human, first has to go through an animal testing. So we need to take ethical clearances from committees, and then we'll put a small piece of our material inside a living animal, maybe a rat, a rabbit, a sheep, anything, it can be anything. So then we'll analyze this, we'll study what is the effect of that material inside a living organism. This test can be carried out for a duration of say 4 weeks, 8 weeks, 6 weeks. That depends upon your implant location. Okay, so after the third step also, we finalize that, okay, the material is not causing any harmful effects to the animal also. Then we have to go for the clinical trials, that is the real human trials. Now also the material is not fully commercialized. We cannot say that, okay, I have material A which can be used as an implant. But we have reached the end level where we can test it with humans, and we can be sure that since we have passed all the other levels, we are certain that this can be used as a material. So as a final conclusion, we need to try it with humans. So once it is implanted in humans on trial basis, and this is certified that, okay, it is not causing any problems, then only we can say that material A can be used as a suitable implant material. So this is a very big procedure. It may take up to 5-6 years, depending upon what is your implant location. If it's a normal small implant, tooth implant, it may take a little bit of time. But if it's a very complex body part, or if it's a complex procedure which needs to be adopted for implanting it, it may take a lot of time. So this is the general criteria. There can be subdivisions into this. There can be detailed division of each and every part. So we'll not go into that, but this is the overall broader perspective of how a selection criteria is taken out. What are the types of biomaterials that is available? So we have pure metals like iron, magnesium, titanium metals. We have alloys of like stainless steels, is an alloy of iron, titanium alloys, cobalt alloys, chromium alloys, so on. We have ceramic materials. Ceramics are basically used as your tooth filling. We have hydroxyapatite, we have tricalcium phosphate, we have alumina, and so on. Then we have biological materials. We have bovine wool. Bovine is cow. So I'm not sure if you have heard of it, but people there are cases where cow's valve has been used as a substitute for human valve, human heart valve. So that is exactly a biological tissue from an animal which we are putting it inside your human body. Similarly, we have porcine valves. Porcine is pig. Pig valves are used. Then we have venous grafts. Venous grafts are like sometimes what happens is that in heart, a particular artery may be blocked way too much beyond the scope of repair. We cannot put stents also. So at that point, what we do is, what doctors do is, they take a piece of vein from your leg or thigh. Now, veins, we know, they carry deoxygenated blood from your body parts to your heart. So they are not as important as arteries, though they are very important, equally important, but a little bit lesser important as compared to arteries. So what they do is they'll take a vein from your leg or thigh, and they'll bypass that blocked arteries using a vein from your own leg. So that is called venous grafts. Then again, we have polymers like PMMA, PET, PTFE, and so on. So these are the basic materials that are used as possible biomaterials. Now, the properties which we may need. Hello? Hello?
Yes, yes. Vignesh, you carry on.
Yeah,
Yes,
okay.
yes.
So,
Yeah, it is audible.
yeah, right. So the general properties that we encounter that we need for any material is like for alloys. And why do we go for a metal instead of a polymer? For metal, we need strength, we need ductility, we need hardness, we need it, easy machinability of it. Now we need it to be corrosion resistant. Now one of the disadvantages with body is that inside a body we have lots of solids, so salt composition. We have chlorides, we have sulfates, we have hydrocarbons, we have carbonates, so many ions, salt ions. All these create a corrosive environment for any metal. So our material should be corrosion resistant to all these things. So that is one of the important criteria for metal and alloys. When we go for polymers, those salt may not react with polymers as compared to your metals. So polymers are better as compared to your metals in terms of corrosion resistance. But the issue with polymers is that we may not get that level of strength. We will never get 120, 150 or 180 gigapascal for a bone implant when we compare with metals. So that level of strength is not reached in case of polymers. But again, polymers are nothing but carbons, nitrogen, hydrogen, oxygen. So those are all hydrocarbons, and those are all parts of our body. So it is highly biocompatible. And as compared to metal, it is quite cheap, polymers. When we go for biological materials, like I said, we have heart walls, we have pig walls, cow walls, all those things. They're highly functional. Functional means like heart walls, it was prior also, the valve was inside the heart pumping blood for you. Now when you replace it inside the human also, the functionality remains the same, almost same, except that the surrounding tissues may differ or anything like that. So functionality remains the same. So because of that, the biocompatibility is very high. But the only problem is that we need expertise to handle such things. We need expert surgeons to handle such implants. We need expert doctors to carry out the transplant procedures. Plus, while taking out the wall from a cow, we need to ensure that it does not get damaged or it does not get clotted or all those things. So there are a lot of complications that is involved with handling of biological materials. Now, when we come to ceramic, yeah, of course, hardness of ceramic is very high. It is highly biocompatible. One of the good things with ceramics is the aesthetics. Now, we don't want a silver filling or a black filling in our tooth. People will say you still have a cavity in your tooth, but we only know that it's not cavity, but it's a filling. So what we need, we need something which is white in color to our tooth. So those things can be easily achieved with ceramics. We have that after root canal, doctors place in a cap on your tooth. So those caps can be made up of your steel, but above on the steel we have some white porcelain or some white ceramics so that it matches our tooth. We have zirconia, which is very hard and which gives you a tooth substitute. So these are the some of the basic properties of the materials. Now applications. Now there are lots of application of biomaterials. Starting from top of your head till your foot, you can see that the materials can be used anywhere. It's used in eyes, it's used in bones. We have maxillofacial reconstruction. We have broken jaws, and doctors are using screws and bones to repair that. We have heart walls, spines, orthopedic applications, blood vessels, even polymers, nylon tubes and polymers are used as substitutes for your blood vessels. Uh, like in one case, say we are going for a total heart replacement surgery. So what we need to do is we need to pump the entire blood out and we need to circulate that blood till the time the heart is being replaced. So for that duration of time, we need a biocompatible tubes which can help us circulate the blood. So those things are very important. We have bone fixation, we have nuts and bolts and screws and so on. So the variety of biomaterials is extensive. This image is not exhaustive. We have so many other applications which may not be shown in this image. So I mean, if we go into greater depth and greater detail, we'll understand that there are a lot of things that we still need to cover in this. So this is the broader perspective of what is the biomaterial. So like this is your heart valves. These are the cardiovascular stents that are used. Now these are your eye lenses. These are not contact lenses, but the lenses that are used with retina, eye lenses. So you can see the scaled image, how small it is. These are, I guess, polyacrylates or some polymers. Now these are bone joints that we are having. These are the screws and plates that are used for bone fixation. So this is the general idea of a biomaterial. Now you may ask, the current research trend is degradable biomaterial. Now what is degradable biomaterial? Now as the name suggests, it needs to degrade. Degrade means it should wash out, it should corrode inside our body. So something which is a biomaterial, that means which is biocompatible and which can be used as an implant, it should degrade inside a body. So that is the general term, that is the general idea of degradable biomaterials. So the implant degrades inside the body after a particular period, assisting in the tissue healing or other clinical needs. So it should not like we are placing a implant inside the body and say within 3 months it degrades. So that is of no use, because then again within 3 months definitely no bone will heal or no tissue will heal. It needs some time. So that material should withstand, we should be inside the body for that period of time to assist the healing. Now the other issue with degradable material is, say for example, I am having a steel inside a body. Now steel will not degrade. Say if I am having iron inside a body. Now iron, when reacts with your corrosive fluid, it will produce iron oxide, it will produce iron hydroxide and so on. Now all those effluents, all those degradation products, that should not cause a problem to the body. Now in the previous case, what we saw was that the implant is permanent. Now stainless steel or titanium implants are permanent. They will not degrade. But there also what we wanted was that it should not react with the body. But now in this case, what we want is that it should react, because we need a degradable biomaterial. But the degradation product should not react with the body. It should not increase the toxicity of your tissue or bone or the whole biological system. So it should be either absorbed by the body or it should be excreted out without any problem. Even during excretion also, it should not get deposited in your kidneys or intestines or anything. So there are a lot of parameters that we need to ensure before understanding this. Again, this is a temporary application. We say that we need a material A which should help us in healing for up to a period of 2 years. After that, it should gradually degrade. So it is a temporary application. Now we cannot use this for everything. Total hip joint, it may not be suitable for a total hip replacement, or it may not be suitable for say your eye lenses, because we need that to be permanent. So this is not suitable for all implants. Now what is the need for a biodegradable? We talked about what is biodegradable material, degradable biomaterials, but what is the need? Now it avoids trauma to the patient. Now patient already have undergone a surgery to get a bone fixed into his body. Now after say a particular period of time, that bone is fully healed and it needs to be removed. But then again this patient is to undergo surgery and then that plate needs to be removed. So that puts a trauma to the patient. So we need to avoid that. And what doctors say is that the presence of a permanent implant inside a body is not required, because eventually that will cause problems. So this avoids the presence of a foreign body inside for an object inside the body. Now, when we talk about the degradable biomaterials, in some cases it creates reactions with the body. Like for example, stents. We have stents. So the issue with stents was that initially it helped us solve the problem of atherosclerosis. But over a period of time, the body started reacting with it and it causes inflammation, it causes clot formation, thrombus formation, and so on. So late reactions may occur in case of permanent implants. So we need to avoid that. And like permanent medication is required. Sometimes the patient needs to be on permanent medication because of an implant. So that like antiplatelet, the patient needs to take antiplatelet medicine, the patient needs to take blood thinner medicines, and so on. So that can be avoided after a particular period of time. So that is the main reasons why we are going for degradable biomaterials. What are the materials? We saw that we are using metal, polymers, composites, etc. for a permanent implant. So what are the materials that we are going for in case of degradable materials? It's the same. We have pure metals, we have polymers and alloys. As of now, the extensively worked on material is magnesium, iron and zinc. We are having these as pure metals and its combination alloys which can be used as a degradable metallic material. Why we are going for these materials? Because the degradation product of say magnesium or iron, they are easily absorbed by the body. So it is very easy to use these materials. And polymers, as it is, polymers are highly biocompatible. We have hydrocarbons, we have carbon, oxygen. So even after degradation, those products are not at all toxic to the body. So if you are going to work on say pure on metallic degradable materials, then you have to focus upon magnesium, iron, and zinc as of now. This is the current research scenario. Characteristics of degradable biomaterial: it should be biocompatible, it should be non-toxic, easy disposable of degradation product. That I said, it should get absorbed by the body or excreted by the body. Now, sufficient mechanical strength of the degradable implant. As I said, it should not degrade within 6 months or it should not collapse under load, because we are designing a degradable implant, so it should not collapse under a loading condition or a tensile loading condition. So we have to ensure that it is having sufficient mechanical strength, and it should give enough time to the tissue to heal. This is the one of the main criteria for this. Now, I should have included this slide earlier, but I forgot to do that. So for any biomaterial, what we need to do is various testing and characterization that we need to carry out. So for biological and corrosion studies, we have tensile and compressive. These are the widely used. These are not, again, I'm saying these are not limited to these tests alone. We have a lot of other testing procedures also, but the commonly used tests are these. We have tensile and compressive for loading. Then we have, when in case of stents, we need to test its radial strength. That is how much it is expanding under a loading condition. Then we have corrosion studies to ensure what is the effect of corrosive fluids on the implant. We have static immersion, we have dynamic, we have electrochemical corrosion. Then in certain cases, we need to modify the surface of the implant so that it suits the body. So in that case, we have various kind of coatings that we are carrying out. So we need to test that coating also, the coating strength, coating thickness, and all those things. And then finally, SEM and TEM and all these are the basic mechanical and microstructural analysis that is carried out. So this is the mechanical corrosion studies. Now we come to the biological evaluation. Like I mentioned earlier, the first and foremost is the cytotoxicity evaluation. So what is cytotoxicity? So what we'll do is we'll take a cell line. Cell line is nothing but a particular cell which can replicate the body conditions. So what we'll do is we'll put the implant or a particular piece of that material in contact with the cell line, and then we'll see how the cell is responding to that material. So it usually takes 3 to 4 days to analyze what is the effect of that material. The hemolysis is what is the effect of the material when it is in contact with the blood. So whether that material is causing the death of red blood cells or not, or what is the effect of material on the hemoglobin content and all those things. Antiplatelet adhesion. This is carried out to analyze what is the effect of platelet, whether it is getting adhered to the material surface or not, or what. Then antimicrobial growth, what is the effect of the material on the bacteria or cell, different kind of cells. And finally, animal testing. We have short-term animal testing and we have long-term animal testing. So this is like in vivo testing. So this is the basic idea of what is degradable biomaterial. So what is the current research scenario in case of this? So we have stents for atherosclerosis. This is one of the widely explored area in case of your degradable biomaterials. Then we have screws and for maxillofacial surgeries or screw for your bone surgeries. So we have magnesium screws or magnesium alloy screws made up of used in these positions, in your jaws or in your bone and so on. We have hip joints. People are working in the field of hip joints to see whether we can include something we need, even though hip joints are permanent implants, but certain researchers are working in this field to analyze the effect of degradable implants for this. Then bone joints, plates, and screws. Also, these are the current research scenarios with terms of degradable biomaterials. Now I'll discuss a little bit about the cardiovascular biomaterials or the cardiovascular diseases and what is the material that we are using. So my research was in this field. So, so why I chose cardiovascular diseases? Because cardio heart diseases are one of the extensive reasons for global death worldwide. We have coronary heart diseases, we have heart diseases, heart failure, stroke, blood pressure. So these are some of the common heart diseases that we are encountering every day. I mean, every household nowadays have having hypertension problems. Every household are having people with blocked arteries. So this is a reason for, a change in lifestyle is needed basically to change it. But in some cases, the level of heart disease is so extensive that we need to go for surgeries and so on. Even though we are having good medical facilities worldwide, but the cost of heart diseases and related surgeries are very high. So people are still working on this. People are still working to improve the level of the devices that we have to solve all these problems. So it is one of the biggest reasons for global mortality. India almost has 54.6 million cases of cardiovascular diseases. So that is a lot of numbers. Now, coronary heart diseases like atherosclerosis are the maximum share of CVDs. Now, CVDs we saw that includes your coronary heart disease. It involves your high blood pressure. It involves your everything, stroke and so on. But what is coronary heart diseases? Now heart pumps blood to entire body, but heart too need blood, right? It is also living tissue. It needs blood. So the arteries which give blood to heart itself, those are coronary arteries. So if there is a problem in coronary artery, it is called coronary heart disease. So atherosclerosis, which is the deposition of fat or plaque, is one of the biggest coronary heart disease. Now you must have heard about angioplasty, angiography, and so on. So it was a very successful. If I'm not wrong, it was introduced in 1960s or early 70s, the angioplasty. So since then, this technique is still being used, but it is not as successful as it was. There are certain cases where a patient goes in for angioplasty, but when he comes out, the arteries collapses again. So there are chances of reoccurrence of blockage in the arteries after angioplasty. So like almost 30 to 40% of cases of angioplasty failed. So we needed a solution to this. So what was the solution to this? Okay, so let me tell you what atherosclerosis is, just one slide. So it is nothing but the blockage of arteries due to deposition of fat. Now what happens is that we have a healthy vessel through which blood is flowing. But what happens is that the vessels start narrowing down because of deposition all around the walls of the arteries. So gradually the deposition increases and a particular point reaches where the blood flow is so restricted that it puts extra pressure on the heart. The heart needs to do extra work to pump the blood. Eventually what happens is that it causes a heart attack. So this is what the atherosclerosis means. So you can see like in the first image is the heart lumen. We have small deposition, but gradually the deposition is increasing and increasing. So this is what causes the load on the heart. So what is the solution to this? Stents, cardiovascular stents or endovascular stents. So what are stents? Stents are nothing but small tubes or mesh. It's like a spring. You must have seen the springs in your pen and pencil. So it was something similar to that, but a different kind of pattern. And now in the image, you can see that we have spacings all around the stents. This allows the blood to flow through it. So what people do is that they put the stent inside the blocked artery and they expand it using a balloon, and then they pull out the balloon. So the stent sticks to the wall of the arteries in the expanded position and allows the blood to flow. So this is the general concept of a stent. Now stent again, like it says 1986 was the year in which first stent was implanted, and since then stent has gone through a tremendous amount of improvements. Earlier stents were called bare metal stents because they were simple metals, stainless steel stents placed inside the body. Then they had some issues with bare metal stents. Then what they did was that they coated drug on the stent and then they implanted inside the body, but again that had some issues, and now currently people are working towards degradable stents, degradable metallic stents. We have degradable polymeric stents also, but again there is an issue with polymer strength as compared to your metal stents. Now, magnesium, as I said, magnesium and iron are two of the important materials that is being used for your research in case of degradable materials. For stents also, people have tried different kinds of magnesium alloys. We have tried different kind of magnesium iron alloys, coatings on magnesium, coating on iron. People are using powder metallurgy techniques and whatnot. A lot of research is being used in this, but still a viable, commercially available degradable stent is not available. Is yet to be received in the market. Though a company is claiming like this Magmaris, it is one of the reabsorbable magnesium scaffold by Biotronic AG Switzerland. So they are using, I mean, they got the approval for clinical trials and they are doing it, but somehow, I mean, the outreach of degradable stent is yet to be received. People are still working on it and still a lot of improvement needs to be carried out. So, like I said, metals and polymeric materials are used for degradable stents. Magnesium and iron-based alloys are the prime candidates, but still no commercially viable solution is available for degradable stent. Now, you may ask, why do we need a degradable stent? Now, like I said, presence of a permanent implant may cause late reactions. So, when the bare metal stent was placed, what people saw was that it is causing irritation, it is causing thrombus. Thrombus means clot formation, and so on. So in the second generation, what people did was that they coated certain kind of drugs onto the stent and then they placed it. Now those drugs are very efficient. They did not let clot form. They did not allow irritation or inflammation. But the amount of drug on the surface is limited. After say 2 or 2.5 years, the drug washed out. The drug depleted. Now again, that stent is a bare metal stent. So after say 3.5 years, 4 years, people are encountering issues of irritation, thrombus formation. Now you have to keep in mind that this is not the 100% case. This may happen in say 10% or 15% of the cases, but still people are encountering this. So that is why to encounter this permanently, people are thought of going for degradable stents. So I mean, I'll stop with this. I hope you got a little bit insight of what is biomaterials or what is degradable biomaterials. If anyone is interested, you should go and read these two books. It is the first one, the Introduction to Materials in Medicine, is a very excellent book. You have to go through this. You can find everything about biomaterials in this, and it will help you a lot. So I'll stop with this. If you have any questions, you may please ask.
Sir, we will be getting a copy of this PPT if you don't mind.
Yeah, sure. I'll email this to Professor Maharajan. You may take it from him, sir.
Okay, sir. Thank you, sir.
Yeah.
Sir, hello, sir.
Hello, sir. Yeah. Please tell me,
Yeah,
sir.
sir. Myself, Sarnagar Diksa. I am working from PACR Polytechnic.
Okay, sir.
I am the role of lecturer.
Yes, sir.
So I am one of the biology student for this field also.
Okay.
So I want to some more little bit questions from you, sir. Can you ask
Yeah, sure.
some
Please go
questions,
on.
sir?
Go
Okay,
on.
sir. What kind of standard to be used to biomaterials, sir? What is
Now,
the standard?
standard as it is, we do not have any standard per se for biomaterials. For testing, we have different standards. For biological
Okay,
testing,
sir.
like I said,
Sir,
cytotoxicity.
I will asking you one more standard, sir. 13485 is the medical related things.
Okay. No, yeah.
Uh, I will ask the question,
Yeah.
sir. It is the medical related standard, sir. 13485, I think. ISO.
Okay, so no. What I am saying is that for carrying out the testing procedures, like for cytotoxicity, we have certain guidelines from ISO. So for hemolysis, we have certain ASTM standards, we have ISO standards for all those things. So for carrying out the testing procedure, we have standards. Now, like you mentioned, we have some biomaterial standards. So, I mean, definitely for commercialization, we need to encounter all those standards before proceeding with it. But
Okay, sir. And one more point of view, sir. Generally, steel is the corrosion material, correct, sir? We have to contend with the moisture, some chemical reaction should be happen.
Yes.
What I am saying the questions in our human body, inside the human body, some water will be flow. That's acid also will be there, hydrochloric acid. It will be react with the material in our biomaterial. Any kind of reaction will be happen.
Yeah, so it depends upon the implant position. Now you are saying that acid is produced. I'm sure acid is not flowing through your arteries, or it is not present at your bone implant. It is definitely inside your intestine or your stomach. Okay, so when we put it inside say arteries, we have blood, we have plasma, and we have all the body fluids. So it will react. It will, if we are going for permanent implants, say titanium implant, we have titanium stent, or we have.
Sir, why I am the question from this one? Because that metal will be react means the permanent it should be installed in the body or a temporary basis or reworked one.
That's what I'm saying. It totally depends upon your implant location. If you are going for a titanium hip joint, it is a permanent implant. So it should be corrosion resistant. But if you are going for a temporary cardiovascular stent, it may not need to be a permanent implant. You're getting me? So it totally depends upon your implant location, where we are putting it, the implants.
Generally, material is ferrous and non-ferrous. Correct, both of them there.
Magnesium.
So in this case, non-ferrous material only used or ferrous also can be used, sir?
Yeah, that's
for this case.
For degradable materials, magnesium and iron are used because they are getting absorbed by the body without causing any side effects. People are looking into zinc also, but magnesium is extensively used because the magnesium hydroxide is produced, magnesium oxide is produced. So that is getting easily absorbed by the bones and tissues or easily excreted out via urine. So that's not a problem. But say if you are using anything like silver causes microbial reactions. It is antimicrobial, so it may increase toxicity of your body. So depending upon that, we have to decide. Iron is also used because iron oxide, iron hydroxide, those are easily absorbed by the body.
So that is the non-ferrous material, correct, sir?
Magnesium is non-ferrous material. Iron is a ferrous material.
Okay, sir. Okay, sir. Sir, and one more point of view. And generally, the medical devices all are plastics, I think. So any kind of plastic material can be used to this treatment also.
Yeah, polymers are widely used. Polymers, as I said, polymers are used in your tooth. I mean, your eye lenses are made up of polymers. Certain kind of stents are also made up of polymers. We have nylon, which are used. So PTFE, which are used. So polymers are also widely used. It's not restricted only to metals alone. Polymers are also used. But the point is, when you are going for a load-bearing application, we cannot use polymers for a bone joint because load will be high over there. So we have to, again, the main concept is, like I showed in your first slide, the application-oriented testing needs to be carried out, where you are putting it. After biological characterization, we need to ensure that wherever we are putting it, it should meet the standard of that location.
Okay, sir. And one more point of view, sir. What kind of process going on ceramic system? How to produce, sir? Any kind of process will be there, sir?
Prediction, I didn't get you. What kind of prediction you are saying?
What kind of process, sir? How to manufacturing the ceramic material?
Okay, like for example, hydroxyapatite, one of the most common ceramic material that is used. Okay, so we have procedures, we have protocols for preparing hydroxyapatite. We have to mix different chemicals and do it. Or commercially also hydroxyapatite is available. So procedure is simple. It's a totally chemical process. So we can produce it and we can coat it or we can use it directly also. So not an issue. So similarly, calcium phosphates are also there. So there are certain literatures which deal with production of calcium phosphates alone. If you can go through it, you will understand how different kind of calcium phosphates or hydroxyapatites are produced.
Okay, sir, sure, sir. And last my question, sir. In this case, finally, any testing analysis software packages will be there, like that eMatrix or Agile. It is kind of any software packages will be there, because we are going to directly hardware testing means it should be react with some problem also. Before that, we have to analyze any simulative software will be there, sir. In this case.
I'm not sure about software for biological evaluation, but again, for mechanical evaluation, you know what kind of load is acting, tensile or compressive. So you can do the mechanical analysis in any of the software. For corrosion studies, we have different kind of softwares for corrosion studies alone. So, but I'm not sure about biological evaluation if there is any software for that or not.
Okay, sir. 3D, 4D printing, in these
Yes,
cases,
yes,
any
yes.
used for biomaterial?
Yeah. 3D printing is also extensively used. 3D printing are used for making those, like I said, polymers. You are making polymer screws of 3D printing. We have stents made out of 3D printing. So everything is being 3D printing is one of the upcoming collaboration of your biomaterials with mechanical engineers. So yes, 3D printing is a viable option. You can study that also.
Okay, sir. Okay, thank you so much, sir, for your
Thank you. Thank
wonderful.
you. Yeah.
Thank you, sir.
Hello.
Thank
Hello.
you.
Good evening, Vignesh sir.
Good
I am
evening, sir.
Anil Kumar.
Yes, sir.
How
Please
are
tell me.
you?
I'm fine, sir. How are you?
I am very fine.
Yes, sir.
For hearing your voice, I attend this program.
Okay, sir.
I have one general doubt.
Yeah, sure.
Uh, how to evaluate that degradation time, sir?
Okay, it's a very good question because one of the common problem that we face is that how to control the degradation rate. So for that, we need to find first understand what is our base degradation. So for if you go through literature, you will find that people have quantified that for say stents, we need a minimum period of 12 to 24 months. That is the time period that is needed to for the healing of your arteries. So let us assume 24 months is the minimum period that we need. Now, if I am going for a material A, say my material A has qualified all the things. It is biologically inert, it is mechanically stable, everything is okay. Now I'll do corrosion studies. We have immersion. I showed you the slide, immersion test. So what I'll do is I'll prepare a simulated fluid. That fluid resembles your blood. It's not blood, but it has constituents of a blood. It has dissolved salts of blood. So what I'll do is I'll make 5 to 10 different samples of my material A, and I'll put each in one the solution, and I'll analyze it. I'll monitor it for a period of say 30 days. So for 30 days, I'll see what is the effect of body fluid on that material. So from 30 days data, I can extrapolate it up to 2 years. So then I can find out, okay, whether this is going to corrode or not within 2 years or more than 2 years. So that is how people are extrapolating data. And there are corrosion software models also, where we have to put in the density of your material, the density of your solution, the dimension of your material, and so on. So from analysis point of view also, you can do it. But if nothing is happening, you have to go for a totally experimental view, then you have to wait for 2 years. No other option.
Okay, sir.
Yeah.
And in that, we are maintaining some temperature and dynamic motions inside the body. We are having a dynamic fluid, and temperature is also there. Those things also affect the
Totally.
materials.
Temperature will affect, your pH will affect, and your dynamic motion, like you said, it will affect. These are all parameters.
How to recreate that environment while testing?
Again, that depends upon your location, implant location. Say, for example, what I did, I carried out the stents test. So I maintained a pH of 7.4, that is the blood pH, with the temperature of 37 degrees. So that was constantly maintained in a water bath. We had to keep a pH meter constantly to check variation in the pH. If there is a modification in the pH, we need to adjust it using buffer solutions. So this is a constant monitoring. You have to carry out extensive experiment carefully, because if with a slight modification of pH, again the values will change. Because if pH changes, your corrosion rate will change. So again, closely monitor it, and then you have to carry it out.
Right. Okay, sir. Thank you.
Thank you.
Thank you. Goodbye.
Any questions, sir, from any participants?
No, sir.
Okay then.
Okay. Vignesh, sir.
Thank you, Professor Maharajan, for this opportunity.
Yes, sir. Yes, sir.
And I hope that people learn something from me. So
Yeah, definitely, sir.
if we could get a feedback, and if they are interested, we can have a session in future also with an advanced session to this.
Yeah, definitely, sir. I think it's a fantastic and very nice presentation, sir. From you, it's very clear and very informative. The session is very informative. Your research is also very, very good in very tough field. You have done very nice presentation, and most of the participants giving very good feedback about your presentation and your research work.
Thank
I
you,
think
sir.
hope you are having very good future.
Thank you, sir. Thank you. But I
Yes.
must say that if people are interested, you should go and pursue this field because it's an excellent field with a lot of opportunities, even career-wise. If you are able to go good research in the other industries which are willing to take research people who are willing to work into this field, because it is still wide open. People are needed. People are required to work into this. And I mean, it's just the beginning. You have to just go and read a lot. Like I mentioned, these two books. Please share this PPT with people if they are willing. You can go, these two books are excellent. You will get all the entire details from these two books. That is good enough for you.
Yeah, yes, sir. Thank you,
Yeah.
sir.
Thank you, sir.
Uh,
Thank you.
yeah, thank you, sir. Once again, on behalf of Ramco Institute of Technology, our principal, vice principal, and HOD and staff members, and the Indian Welding Society, our secretary, we actually thank our expert speaker, Dr. R. Vignesh sir, Anna University CG campus, Chennai. And also, I sincerely thank all the participants because they are spending 1 hour almost. They are eagerly, interestingly hear your speech and gain lot of knowledge in this particular field. So I sincerely thank all the participants. It's very important, and I once again thank you all. I will feedback link I will give in the chat box. You just click it, and the feedback link will open. Once you submit, you will get the certificate to your mail ID immediately. Okay, one minute. I will.
I'll log out, sir. Then.
Yes,
Sir,
sir. Yes,
thank
sir.
you, sir. Wonderful
Thank you, sir.
presentation, sir. Thank you.
Thank you, sir. Thank you very much. Thank you.
I have post my feedback link, sir. You just click it and fill it.
Okay, sir.
Anything you can write, you can type it, and we will clarify, sir.
Sir, I've sent the feedback, sir.